Thanks so much for coming to my presentation. Today I'm going to talk about some research I recently did into browsers. So I'm Natalie Silvanovich, and I'm on Project Zero at Google. And I've looked at a lot of stuff that's browser related. I've spent a lot of time looking at JavaScript and other JavaScript-like languages. But recently I found myself thinking about what the other attack surface of the browser is. What things exist that are in browsers that attackers haven't looked at a lot? And there were two specific things, WebAssembly and WebRTC. So today I'm going to talk a bit about how I looked at both of them and what I found out. So let's start off with WebAssembly. What is WebAssembly? Well, WebAssembly is an assembly-like format for writing code in JavaScript. They created it for two reasons. One of them, believe it or not, is security. One of the ideas behind WebAssembly is that it's supposed to be an alternative to installing native code on your host. So the people who are creating the WebAssembly standard hope that one day, instead of installing programs on your computer, you might have a WebAssembly VM and be able to run stuff that way. It was also created because JavaScript has some inefficiencies, especially in doing math. JavaScript is not strictly typed, which means that when you do math, you have to check that every value is actually an integer every single time you add it. And this makes math more difficult than it needs to be. So WebAssembly also hopes to create a quick way to do math in JavaScript. A major goal is compilability. So right now, you can compile C++ into WebAssembly really well using a transpiler. And there's some other languages that work okay, but then there's some languages like Java where there's a whole lot of Java that you can't compile into WebAssembly right now, specifically because of garbage collection. And that's supposed to be a short-term thing. The long-term goal of WebAssembly is for you to be able to compile any code in any language to run in your browser. It's a W3C standard, and I think it's a very ambitious standard. They have a lot of goals with it that haven't happened yet with regards to being able to run basically any code anywhere. And it also has applications beyond browsers. To give an example, the Ethereum interpreter is going to move to being in WebAssembly soon. So when you think about something like WebAssembly, there are two possible problems that can happen. Number one is that your WebAssembly engine isn't implemented securely. Maybe someone can put malformed WebAssembly into your engine, and they can corrupt memory and get code execution. That's one problem. There's another problem, which is that code written in WebAssembly isn't implemented securely. Maybe someone writes a buffer overflow in WebAssembly or cross-site scripting in WebAssembly. So today I'm going to talk about this problem and not that problem. And if you're interested in the second problem, which is writing secure WebAssembly, I'd recommend watching the video of this talk from Black Hat. It has a lot of good content on the subject. But I'm specifically focused on the first problem, which is the security of the actual WebAssembly engine. So to start off, what is WebAssembly actually in the browser? Well, it starts off as a binary, and in JavaScript, this will end up being an array buffer or a typed array. And you can load it using a keyword fetch in JavaScript. And then you get an array buffer like this, or an int array like this. Or you can just do what I did and put in every byte by hand. Now, what is this format that you're actually putting into this buffer? Well, it's the WebAssembly binary format, and it consists of a number of sections that have a name and a payload length and that sort of thing. And these sections represent different things. For example, there's one for data types, there's one for import, there's one for functions. I'll go through what a lot of these do later. Another important thing to remember is that there are some restrictions on this. So there are some sections that you have to have, and there are some sections that you can't have more than one, and there's some sections that have to go in a certain order. For example, the type section has to go before the function declaration section that uses those types, that sort of thing. So what happens once you have this binary format in your array? Well, then you create a WebAssembly module like this. And what does this actually do? Well, it parses the WebAssembly and basically loads it into memory. And what sort of problems could this have? Well, there was this bug. And what happened here is as I said, there needs to be a specific order of certain sections in WebAssembly. And this was in WebKit. This is how they actually validated the order. And you'll notice there's a type of section called a custom section. This is basically a section type that doesn't exist yet. This is how they basically ensure backwards compatibility in the future when there's new section types. And it turned out that when they checked the section order for a WebAssembly binary in WebKit, every time you had the section custom, it would return true, which would basically reset all the tracking of ordering. So this basically meant you could have like any number of sections in any order. You could completely bypass this check. And what ended up happening is this actually created a lot of different problems, but the one that ended up being exploited was actually by some other people who found this very same bug for Pwn to own, but then I reported it and they ended up having to use a different bug. They exploited it by looking at the fact that certain arrays in WebKit would assume certain sections only occurred once, even though they could occur more than once. And then you could just write outside of the vector if you had more than one section, because you would overflow the allocated memory. And this turned out to be an exploitable bug. Here's another bug that happened in WebKit. This is also in just loading this module. So in JavaScript, there are array buffers and typed buffers, like this int8 array buffer. And what these do is they're basically just views into an array. So it means that you can look at an array at offset, say 700, but when you index this view, that'll actually be index 0. So the way this bug worked was they forgot to, or I guess they didn't forget to, they accidentally added the offset into the buffer twice. So this didn't even work. If you had a typed array buffer instead of an array buffer, your WebAssembly would never run correctly. And I'm not sure why this wasn't tested, but this actually also caused an out-of-bounds read, because if you were looking at offset 700, it would actually look at offset 1400. So this was kind of a funny bug that allowed out-of-bounds reading. So what happens when you're done this parsing? Well, then you create what's called a WebAssembly instance. And this WebAssembly instance loads basically everything external from JavaScript that's needed to run your WebAssembly. Specifically, it loads imports, initializes imports, and creates exports. And what does that actually mean? Well, there's 3 types of imports, and these are all things you can import from JavaScript. There's functions, there's memory, and there's tables. And I'll explain what these mean in a second. But to start off, I'm going to give you some WebAssembly terminology that you can totally use to impress all your WebAssembly friends. So instances can have the same memory and the same table. And if they do, they're called in the same compartment. And you might think, well, since instances can have a memory and a table, can they share the table but not the memory, or the memory but not the table? Can they be in half of the same compartment? And the answer here is yes, but there's no reason to do this. This is allowed by the standard, but no language you would ever compile would ever generate code like this. But of course, it's still available for attackers to use if they want. So, what are these types? There's first the WebAssembly memory, and this allocates all the memory that your WebAssembly can use. It has an initial and a max size, and it can be expanded by calling grow in WebAssembly or JavaScript. And then you can access this memory using WebAssembly instructions. So here's how you create memory in WebAssembly. You've got the initial size in pages, the maximum size, and then you can just grow it as you need more. And keep in mind, you can only have one of these. Right now, WebAssembly allows exactly one slab of memory, and that is all your assembly code gets. So what can go wrong here? Well, there were 2 interesting and surprisingly similar bugs found in both Firefox and V8. They were both basically that when you grew your WebAssembly memory, it would overflow the integer, cause integer wrap on the integer that showed the memory size, and then they would actually get smaller. And it's kind of funny that both of these bugs happened in different browsers because they were so similar. But I guess that just shows that integer wrapping is a problem and people forget to check for it. Now, one thing I wondered about is, can there be out-of-bounds issues? Because one thing that I really wondered about this memory format is you have this one page, but what if your instructions try to access out of this page? And surprisingly, there were not very many bugs like this, and there are a few reasons why. To start off, there's a limited set of WebAssembly instructions. There's actually only about 6 instructions that access memory. There's load, read, or load, store, and something they call T, which is basically store and return the value. So this is a very small set of instructions that it can actually be audited pretty easily. There's also limited threading in WebAssembly, and this might change in the future, but right now there's no threading, which makes it, once again, fairly easy to audit these instructions. And now they also do something which I think is really cool, which is called safe buffers or signal buffers. And what this is, it only works in 64-bit, is that every time you allocate WebAssembly memory, they map 4 gigs of memory. So basically, they map the entire pointer space from 0 to FFFFFF in 32 bits. And then the memory you actually are going to use, it will map in at the beginning of that huge buffer. And then when you index into that memory using an integer, which is all that WebAssembly supports, it doesn't matter what the integer is. It will either hit valid memory, or it will hit this unmapped section and throw a signal or an exception in Windows. And then the JavaScript engine can catch that, and then they'll tell you you're out of bounds. So this is really nice, just because A, it's really hard to mess up. If you can make your pointer anything, you don't have to do any pointer math to make sure they're not going out of bounds. Worst thing that happens is just they crash due to unmapped memory. And the other nice thing about this is this puts all the performance impact of checking on the people who go out of bounds. If you never go out of bounds in this scheme, you will never hit a memory check, and you'll go really fast. If you go out of bounds, this becomes super slow as they generate the exception, but kind of who really cares when you're doing something invalid and going out of bounds? So I think that's a cool feature that reduced bugs a lot, though unfortunately it only works on 64-bit, so I think it's more likely there will be overflows in WebAssembly in 32-bit. So, the other thing that is supported in WebAssembly is tables, and these are basically function tables, and they can contain other WebAssembly functions, but keep in mind they don't have to be in the same compartment. Any WebAssembly function can go into a table. And tables can be changed dynamically, which is once again an unnecessary feature. If you're compiling code, you will never have your tables changed after you first create them. But if you're an attacker, you can change them whenever you want. And they grow similar to a memory page. You start off with an initial size, and then you call grow. So what could go wrong here? Well, there were also some overflows in expanding the table. In Firefox, there was a similar one to the one with the memory, where you could expand a table until the integer wrapped, and then you'd write out of bounds. And then there was kind of this interesting one in Chrome. And this one was due to basically JavaScript bindings. If you made the index an integer with 2 string defined or 2 integer defined, it would call that and expand the memory, but would still be pointing to the old memory, and you could write out of bounds. And that's a very typical JavaScript issue. And that's just something interesting in that it goes to show that WebAssembly bindings are JavaScript. They can have WebAssembly problems, but they can also just have typical JavaScript vulnerabilities in them as well. So what happens after this? You've loaded all your imports, and then the next step is initialization. And there's 2 initialization types. There are data segments, and they're used to initialize the memory in the memory page. And then there are element segments, and these are used to initialize the table. And when I read about these, I was like, yeah, there are going to be so many vulns in this initialization copying. But that turned out not to be the case, and I think part of it is they're very well defined in the specification. They give every single step and every single check you should perform, and it seems like all the implementations actually did that, and they didn't really go out of bounds very often. But something that I did find was this bug, and it doesn't have a CVE because the Chrome team actually found it at the same time I did and fixed it before I filed it. But I think it's pretty interesting. So the problem here is that if you have WebAssembly that calls a function in a table, that calls into JavaScript, that then removes the function from the table, there will now be no handles left to that function, and it will be freed by the VM. And this was kind of interesting, and they ended up fixing it by making it so that if you call into a JavaScript function and you're already in a WebAssembly call, you can't change the table. And this is okay, even though the specification says this is technically okay. No code like this will ever be legitimately generated, so this didn't cause problems. But then I found another way to hit this bug, which is, let's say that JavaScript you call that removes it from the table doesn't just remove it from the table, but creates another WebAssembly instance that uses the initialization function to initialize that table. That would still actually change the table, and then once again you would have this problem, so there was no handles to your function left when you unwound. And they ended up fixing this by actually keeping a handle to the function, which I think is the right solution here. But this was kind of an interesting and subtle problem in memory management in WebAssembly. So what happens after you finish your instance? Well, it's the last step, the one that finally lets you run your WebAssembly. So you create this module, and you create the instance, and then you get your exported functions, and then you can just call them, and WebAssembly happens. So what happens next? Is it possible that there's runtime issues in WebAssembly? Maybe, though I didn't find any. One concern I had was instructions doing the wrong thing. And actually, early in WebAssembly, like right after it was released, tons and tons of issues like this were found. And some of them were security related, and some of them weren't. But now instructions have sort of started to converge on doing the right thing because people have started actually using WebAssembly and reporting when stuff doesn't work. I still think there could be incorrect bounds checking, though I haven't seen much yet. And I think the handling and memory management issue of WebAssembly is actually fairly complex. So I think it's likely there'll be more use after freeze and issues where WebAssembly stops running and they haven't managed the handles correctly. So I think also in WebAssembly, even though I didn't find a large number of bugs now, and there haven't been a large number of bugs reported in it, in the future it could be much worse, and I actually hope they don't end up going in this direction. There's two features in particular that I think are likely to cause a lot of problems. Number one is concurrency. Right now, WebAssembly only uses JavaScript threading, and this makes it fairly safe in that WebAssembly itself does not have to be thread safe. But they're likely to change this in the future, and I think this will lead to a lot of bugs as they try and change these engines that didn't require threading to support threading. And then there's this other feature coming up. Remember how he said they don't have a working JavaScript or Java engine right now because of memory management? Well, they want to fix it by implementing this thing called WebAssembly GC, WebAssembly Garbage Collection. And this will be a feature that allows you to ask for a small slab of memory and have it managed by WebAssembly. And this will make it possible to implement Java, but I think all the good things about memory, like the signal buffers and that sort of thing, are going to go away if they implement this. So I think if this feature does go in, WebAssembly will suddenly start to have a lot of memory management bugs in it. So who knows, the future of WebAssembly hasn't been decided yet, but this is one possible direction, although they may also continue to go in the direction of limited features and attack surface too. So that was WebAssembly, and after that I looked at this other feature, which is WebRTC. And what was interesting about this is I ended up taking a very different approach. With WebAssembly, I went through every feature one by one and looked at how it worked and looked at the code and figured out where the bugs were. And I looked at historic bugs and used them to figure out what sort of bugs happened in WebAssembly. In WebRTC, this wasn't really an option, partially because the code base was so large, there were so many features, and I actually couldn't find a single historic bug in it, not a single historic security bug. So I ended up doing a lot of fuzzing, and I'll describe a bit how that worked. So what is WebRTC? WebRTC is an audio-video conferencing library in browsers. So if you've, say, used video conferencing in Facebook, you've used WebRTC. Any video conferencing you do in a browser these days is probably WebRTC, and it's also in a lot of mobile applications. It was first implemented in 2011, and then it hit most browsers in 2015, And it actually has a good usage rate. But I was surprised when I looked at it. There was basically no security information available, no information on how to file a security bug, no information on how you should patch it, and I couldn't find any historic bugs. So I thought, this would be interesting, even if I found nothing, just because, there didn't seem to be any info available. So how does WebRTC actually work? Well, it's a peer-to-peer protocol, and then it negotiates this connection using something called signaling. So signaling is not defined by the specification. You can do this anyway. And basically, signaling is where you need to exchange two pieces of information to decide what sort of connection you're going to create with the peer, with the person you're going to call. And there's lots of ways you can do this. On a browser, it tends to be done using WebSockets. On something like Facebook, where you already have a connection, they'll just send a Facebook message to the other peer saying, I want to start a WebRTC connection. But once you've sorted out your signaling, then you start your peer-to-peer connection, and your video streaming goes from peer to peer. And this is actually a good way to, or a good potential area for bugs, because if you think about messaging, usually it goes through a server, and what happens there is you risk that your stuff is going to get filtered by the server. Also, if there's a really bad bug, they might just turn this off. But for the peer-to-peer message, it's very hard for the server to filter it. So I thought that was a good attack area. So from a protocol level, this is how it works. On, I guess, my right, this is the signaling protocols. So typically signaling's done over TCP, over SSL, and then in a browser it can be HTTP, it can be WebSockets, it can be a lot of things. What they don't mention here is there's a lot of mobile messaging where they use the mobile message to actually send the signaling. And then on this side, there is the actual stream that sends the video or the audio. And it says UDP here, but it's actually possible for this to be over TCP and a number of other protocols, but usually it's UDP. And then there's ICE, stun, and turn. And these are the three protocols that help you get around the NAT. So usually on a network, it can be difficult to hit one peer from another peer, depending on your firewalls. But these are the servers that will help you find the way that you can talk to the other peer. And then there's different protocols. This is usually, once again, over SSL. And then the interesting protocol is SRTP or RTP, where they actually send the audio and video. And then there's also SCTP that's used to send data over this channel if you need data over this channel. But I'd say that's kind of a less used and less complex protocol. So what was my first idea? Well, I was actually first interested in the signaling, because even though it goes through a server and it's a bit complex, it would be really useful if there was a bug in signaling just because it's interaction-free. You signal before someone picks up the phone, so that would be a nice way to find remote bugs. And when you signal in WebRTC, you use a protocol called SDP, and WebRTC requires you to do this before the person picks up the call, so you're parsing this untrusted data with no interaction. So I used the WebRTC library to create a fuzzer for this format on the command line, and I reviewed all the code, and I found absolutely no bugs, so this turned out not to be a great area to look at. And I also discovered that some platforms implement it separately. Like Firefox uses WebRTC, but they don't use the WebRTC implementation of SDP. And likewise, WebKit, they do use the WebRTC implementation, but they've actually branched quite a bit. So I thought this would also be multi-browser, but this turned out not to be the case. So, scratch that idea, and I moved on to something different. So my next idea was to look at RTP and media protocols. RTP is the remote transfer protocol, and this is the protocol that has all the video and audio packets in it. And then once the RTP is processed, there's media protocols, and then there's the audio and video codecs that actually process your call. And in WebRTC, I noticed they'd actually written fuzzers for OSS fuzz for every single protocol and every single codec. And I thought, this probably won't have any bugs in it, But I thought, well, I'm going to try doing this end-to-end, just in case there's problems where, one parser parses something one way, but then when it gets to the next parser or actually gets used, maybe they haven't actually validated that data right. So I wrote an end-to-end fuzzer for RTP. So I started off by prototyping it. And the way I did this was I altered Chrome to randomly change a byte of every 10th packet underneath the encryption layer of RTP. And then I called one browser from another, and it crashed every 30 seconds. So clearly this was something that was worth putting time into. I learned the concept would generally work, and I got some very shallow bugs that block fuzzing fixed. A lot of these weren't exploitable bugs. There were actually a lot of divide by zero floating point exceptions that happened here, but got them fixed. So then I did part 2, which is I wrote a C++ client that interacts with the browser. And what was nice about this is it was lighter weight. It could run a lot faster, and I could run it against any target browser I wanted. What was good about it is it was a very good representation of WebRTC. Every bug that made your browser crash was a real bug that caused a problem. The con of this, it was slow, but it did find additional end-to-end vulnerabilities in WebRTC. And what happened next? Well, I was filing all these WebRTC bugs with these really complicated reproduction steps. Oh, build the browser, but change the code. Oh, build the C++, then run this server, then run your web page. And the WebRTC team kind of got sick of me. And they said, well, we have this tool that you can use to record RTP in the browser and play it back in this video replay client. And I tried it, and it didn't exactly work. It would work with the default settings, but with all the not default settings, it wouldn't work. So I spent some time rewriting it so that it would have the SDP protocol that you put in JSON, and then it would load it when you tried to replay it. And this actually worked. And this has now been committed to WebRTC mainline. And this was really good. What was nice about it is it was extremely fast, it was extremely portable, it was extremely easy to actually reproduce any bugs you found. The downside is it was not an exact representation of any WebRTC implementation. So I did have an issue with false positive bugs. But it was good. It could also run on multiple cores, so I could fuzz very quickly, and I could also build it with ASAN, which improved fuzzing. And I found a lot of bugs. So let me show you some of these bugs. They're actually pretty cool. Actually, so this bug I found, it was pretty interesting. And I have to say, I've never seen a bug like this before. So I want to give everyone maybe 30 seconds, a minute to take a look at this and put your hand up if you think you know what the bug is.
A problem with the find function there, that it accesses directly the second. Could be a problem?
Yeah, that's exactly the problem. And this is exciting. I've given this talk to other people, and no one has ever got that right before. So that's awesome. That's exactly the problem. Find comes right out of the codec header. So there's no guarantee that you're actually going to find this one, but it still uses it like it was found. So I'd never seen anything like this before, so I looked up what the map iterator find actually does. And it finds the key, but then if it doesn't find anything, it gives back end. And that actually points to the end of the buffer all the stuff is being kept in. So basically, it's a pointer that points out of bounds, and then this code is just using it. So you can basically just change that value to be anything. And then there was another issue, and this one was kind of similar to that one. And this is, once again, the red thing, a value pulled out of the packet. And then it calls lower bound, and this is something that basically strips everything that's lower than a certain value out of a vector. And then that happens, then they erase everything that they stripped out. And then you'll notice at the bottom here, though, they use something that they pulled out of this vector before they called the erase function. So this is once again a use after free. And another thing that's related to basically vectors and different C++ constructs. And it's actually fairly unusual to see bugs like this, or at least I haven't seen that many reported. So I thought they were pretty interesting. Now there's this bug. This bug is a more typical bug. If you start off at the top, you're going through this loop with temporal IDX, and then you're indexing at L. And then where did L come from? Well, you read it out of the packet. And this was a clear size mismatch. They allocated a buffer of 5 for this, but if you read 3 bits, if you think about it, that can go up to the value of 7, so that ended up being just 2 out of bounds. And then there was this bug. This bug I thought was pretty interesting, and it was also like a little bit simpler than I expected. So there's a protocol called forward error correction, and you can send forward error correction packets. And theoretically, they have a limit of 1,500 bytes. So WebRTC just copied every packet off the wire into a 1,500 byte buffer without checking it. But realistically, in UDP, you can probably go up to about 2,000 bytes. So this ended up just being a huge memcopy overflow of a controlled size. So this was a fairly good bug, and one that I was surprised to find in WebRTC. And then there were some kind of less interesting, more typical bugs. There was a use after free in VP8, the decoder. And this, I guess, what was interesting about this one is it affected far more than WebRTC. Actually, lots of things use the VP8 decoder. And then there was this not very good bug in H.264. It was type confusion, in that if something wasn't actually H.264 stream, but then you made it look like an H.264 stream, it would start confusing its type, and this would end in a read out of bounds. But wait, there's more. And this was, I think, the most surprising thing I found out of all this research. WebRTC, it turns out, is used by many, many, many third parties. It's used by Facebook, it's used by WhatsApp, it's used by Signal, it's used by Viber, it's used by Slack. And I put an asterisk here because this is just a stat I made up. It's not based on actual information, but I think it's probably true that almost every mobile device has at least one and probably 4 or 5 implementations of WebRTC on it. And what concerned me even more was that the WebRTC documentation didn't have any guidance on updates. When developers started using this, there was no place they could get updates or no guidance that this is something they should do regularly. And actually, a lot of these implementations have branched now. So I've been working with WebRTC to help them provide better guidance, provide better ways to report bugs and that sort of thing. But there's still quite a few patch gaps in the existing WebRTC implementations, and I hope this gets better. So the WebRTC fuzzing. As I said, this has been committed into WebRTC, not the version I wrote. They told me my coding style wasn't good enough, and they rewrote it. But it is in there now, and you can use this to fuzz WebRTC. I'd encourage you to try this at home. It's pretty easy. You record a stream in the browser, and then you play it back. And then if you fuzz the recorded stuff, if you just alter it, it'll let you try different WebRTC packets on your browser. And this is an area I think needs a lot more work. So, in conclusion, many browser features have limited external security attention. I'm surprised, especially with the WebRTC, but even the WebAssembly, how little public stuff had been written about this. So I think there's a lot of opportunities to look at these features, that aren't JavaScript, that aren't HTML, and find good bugs. I also learned from this that different bug finding techniques work well on different targets. I'm usually the person that reads the standard and looks at every feature one by one and finds bugs that way. But this didn't work out with WebRTC, and this was actually a target where fuzzing worked really well. Another conclusion is both of these projects had a high tooling cost. For WebRTC, I had to figure out the assembler, make a tool that would copy the bytes into the browser and let me change them. For the WebRTC, I had to fix up that video player. Both of these were more effort than I usually put into tooling, but for both of them, it was worth it with regards to finding bugs. So I think I've discovered that effort can be worth it. And I also discovered that both projects could have benefited from more thought on patching strategies for non-browser users. Both of them have people who are using WebAssembly and WebRTC not in a browser for various purposes. And I don't think they thought about what is the patching strategy for these people when they started creating these features. And I think that's something that could have had a great benefit because right now both of them have the situation where there are many unpatched implementations. So that's it. I'm going to have about 5 or 10 minutes for questions, and then I have a set of bonus slides for you.
Here, you said that there are, in the memory allocation of the WebAssembly, a chunk of memory is allocated for the assembly code, right? That it is because of this that you don't have many out-of-bounds problems with a WebAssembly. Does that generate too many memory costs? Like you could have like several WebAssemblies loaded in the memory, and every bit of WebAssembly like getting its chunk of memory and not using that whole memory?
I guess sort of. So you have these chunks of memory, and WebAssembly instances, they can either use your chunk or they can use their own, but every instance can only use one piece of memory. So it either has to completely share the memory or completely use its own memory. There's no opportunity for WebAssembly instances to have like more than one slab of memory. Yeah. Does that make sense?
I think so.
Hi, so with Node and WebAssembly, can we use, I don't know if Node already have implemented WebAssembly, but if they do, can we use it for to get security issues from the server side? I mean, to explore anything?
Yeah, so that's the area that I looked at less. I think the browser side is much more dangerous here in that you're actually processing untrusted WebAssembly, and for things like Node, it's mostly going to be code you wrote. So really you're getting into that second problem I showed on my slides, which is maybe someone will write a vulnerable WebAssembly. And I do think that's a possibility, but it's a very different problem than the issue of untrusted WebAssembly. Any more questions? Okay, I'm going to move on to bonus slides here then. So I'm going to talk a bit about the WhatsApp bug I found, which was an offshoot of the WebRTC research. So as I said, WhatsApp uses WebRTC, but it also uses something called PJSIP. And PJSIP is basically just another WebRTC type implementation. It's also open source, but it's commercial. So if you put it into a product, you have to pay for it. And so WhatsApp combines these two. So the WebRTC issues didn't actually affect WhatsApp. So I wanted to go and find my own bug in WhatsApp. So I looked at the Android app because Android is far more debuggable than iOS. And there were no symbols, but they use libsrtp, which was written by Cisco and is also in WebRTC. And I found the log entries, and I eventually found a mem copy where they copy the packet right before it's encrypted. So I decided I wanted to hook into that to do my fuzzing. So I used a tool called Frida, which, by the way, is completely awesome. And it's a server that you can put on your Android device, and it'll allow you to hook a lot of functions. So I started off by hooking memcopy, and what was nice about it is it was like 5 seconds between starting Frida and hooking memcopy. But it turned out to not work well enough for what I was doing. The problem with these video calls is they're calling like memcopy like many, many times per second, and Frida caused lag. But it was good to see that it was at least getting called, and this actually helped me debug the next step. So my next step was I basically altered this memcopy to call into a library that I wrote. So I overwrote the GIF transcoder because I didn't think I was going to use the WhatsApp GIF transcoder probably ever. And I overwrote it with this function that just DL opened a library I put on my device and called a function I wrote. And then I made the memcopy just point to that function. I totally used an online ARM branch converter to do this, as opposed to doing branch math. But I ended up eventually getting it to work so that it would call my code. And then I was able to basically log this memcopy and change what packets were going to the other device on WhatsApp. So I tried doing this, and I found that my calls disconnected all the time. And then, of course, I discovered my code was buggy. And I fixed it so that I could actually log and alter incoming packets reliably. But I discovered that replaying the packets by pure copying did not work. So I looked at how it worked a bit more, and I discovered that WhatsApp has 4 RTC streams. So the way the RTP protocol works is you can have multiple streams. You can have audio, you can have video, you can have whatever you want, and they have different payload data types on them, and also a different what's called an SSRC, which is just a random identifier, so that if you have like 5 Facebook video calls going at the same time in your browser, they don't collide with each other. So, and on WebRTC, this wasn't a problem because since you could basically control the protocol very well, I just fuzzed all the streams one at a time, and it's really no different than having 4 at a time. But on WhatsApp, you have to have all 4 running at once. And honestly, I don't even know why they have 4. Like, it's 1 for audio, 1 for video, 1 for synchronization, and I'm guessing like 1 for good luck, because I don't know what they all do. But they had different payload types, so I made it so that I would log them separately and play them back separately, and this actually worked. So I replaced my logging function with something that would alter the outgoing RTP, just change 1 byte or replace it with random bytes, or it would just elongate or truncate the packet. It took 15 minutes for WhatsApp to crash, and that was how I found this heap corruption bug. So I think this is the end of my bonus slides, but I just wanted to share with you, this was another offshoot of this browser thing. It wasn't quite WebRTC, but it got me thinking about how video conferencing works on different platforms and what the different bug types are. So I think that's another advantage of looking at these less known features. It kind of opened my mind to features that could lead to remote code execution that I hadn't thought about before. So hopefully you can take that idea away too. Thanks a lot.